All right, so the YouTube site should be streaming now, and I'm confirming that with my own browser. Okay, there we go. So it's up and running. All right, so we're gonna get through an example. So your homework assignment is about Powerball, Super Lotto, that sort of thing. But the example I'm giving you is not about Powerball nor Lotto, because I want you guys to kind of think about it and be able to find what is common between the problem that I'm going through today and what your homework assignment needs to do. All right. So in the homework assignment, you already got some links. You already got a table. So everybody has a different problem to solve. I know this is not going to stop, some of the most die-hard people from getting help, more than usual help, from other people. But hopefully this will, kind of make it slightly more challenging, because when people ask, so how did you solve your problem? At least they cannot just say, okay, here are my numbers and this is my equation. At least they have to go through some explanation of, okay, this is how I solved my problem. And yours is a little bit different. Maybe we have to change some of the numbers in the equations in order to solve your problem. So that's what is happening with the homework assignment. There's a big table. You look up your student ID, and then you get your specific problem description from the row in the table. Okay, so the most important part is most of the problems revolve around computing the odds of winning a particular prize when someone plays the lotto game, with the Powerball. So that particular game or that particular lotto involves having to choose 5 numbers from 1 to 69, and those are called the quote unquote lucky numbers. And then you have one single number that you have to choose from 1 to 20, and that's the Powerball number. And these two are fairly independent. Okay, so whatever number you have chosen for the 5 lucky numbers can also be the Powerball number. In other words, the Powerball number, how we choose the Powerball number is independent to how we choose the other 5 numbers. Excuse me. And we want to figure out, what are the chances, that someone can win a partial prize? Like, what if I have two matching lucky numbers and also the Powerball number? What are the chances, that that's going to happen? And Jonathan said, can you be winners for both? Both of what? You mean winning both the lucky numbers and also the Powerball number? That can be combined. Yes, it can be combined because the jackpot itself is to have 5 out of 5 lucky numbers matching and also having the Powerball number matching. So that's the jackpot. And it is also interesting to observe. Yeah, so it's also interesting to observe that I think now it is more than $80 million. And for the past, I cannot remember how many weeks, there had been no one winning the jackpot, not even close to winning the jackpot. So that's why the jackpot is so huge, because every single time we just kind of stack a little bit more money on top, and nobody has won the jackpot so far. So $80 million right now. But our job here is to calculate a few things. One of those things is what are the chances that someone can win a particular prize. So that's described in the homework assignment. Okay, the homework was already released earlier this afternoon. But instead of talking about the homework assignment, I'm going to talk about something else. I'm going to talk about 2 characters from a science fiction show called Babylon 5. Do you need to know Babylon 5? No. But, in case you're curious, these 2 characters in the show, one is called Jakar and the other one is Londo. They are not humans. Okay, that's why they got some kind of strange names. So, these 2 characters, Jakar and Londo, decide to go through a magazine of space travel, and in the space travel brochure there were 20 destinations. And each person, Jakar and Londo, each person is going to choose 6 destinations out of the 20. So they just go like, oh, I like this place. I like to go to Earth. or I like to go to Minbar, or I like to go to the Shadow Home World, okay, and so on and so forth. So each one is to choose 6 destinations, and but they only get to travel to the destinations that are in this intersection. Okay, so this is kind of relating back to the set concept. So out of the 6 that Jakar chooses and out of the 6 that Londo chooses, if there's an overlap, those are the only places where they can travel to, and those are the rules. So now the question is, what are the chances that they would choose 4 common destinations? So how would you solve this problem? How do you approach this problem? That becomes what we're going to talk about next. So instead of waiting me to give you the answer, think about it a little bit. Okay, how would you solve this problem? How would you approach it? All right. Alright, so Jonathan is saying try to find out whether order matters. Okay, that's a good starting point. And in this case, ordering is not important. So, one person can choose Earth as the first of the 6 destinations, and the other one can choose Earth as the 5th destination. Doesn't matter at all. So, ordering is not important. So, given the ordering is not important, what are we going to do next? All right. Next one is combination without replacement. So yes, so since ordering is not important, because if ordering is important, then we are looking at permutations. But since ordering is not important, we are looking at combinations. Okay, very good. How would you define your event? Remember omega, which is the set of all possible outcomes, and then your event set would be the elements within the omega. In other words, it's a subset of omega, but those would be the events, or those would be the things that you are interested in. So in this case, the things that we are interested in would be, hey, all of the cases, all the possible cases where Jakar and Londo would choose 4 common destinations. All of those are special to us. Okay, so what are we going to do next? Let me just kind of jot down some notes here, because you guys have made some very good points already. So since ordering is not important, count or use combinations. Very good. Okay. And also there's one more thing here, without replacement. Okay, and without replacement. In other words, we cannot choose Earth 6 times. Okay, you can only choose one destination up to once, and then you have to move on to another possible destination. Okay, so what else are we going to do? So we have to think about event and omega. Okay, so think in terms of E, which is the event, and think about your omega, which is the set of all possible outcome. Okay, and of course now the question is, let's deal with omega first. Okay, omega is actually the easy one to figure out. Yep, so we want to find out what is the cardinality of omega. So what do you think is the cardinality of omega? So this gets a little bit tricky, okay, because it's a matter of perspective. Okay, it is a matter of perspective. So let's not look at the overall problem omega. Let's just look at one person. Okay, so focus on, okay, I'm gonna write here, focus on, I'll just pick one of them, okay, Jakar, okay, and think about how Jakar can choose one destination, oh sorry, not one, but 6 destinations out of 20 potential destinations. That's a pretty easy problem to solve. So I'm gonna let you guys solve this problem. What number are we looking at? We know we are dealing with experiments. So think about each destination that Jakar is going to choose. Okay, each destination chosen is one trial in the experiment. and the experiment has 6 trials because we need to pick 6 destinations, without replacement. So we cannot have the same destination appearing more than once. So if we just want to count the number of ways that Jacquard can choose 6 destinations out of all the 20 potential destinations, what are we looking at? Jonathan is correct. We're looking at 20 choose 6. I think the numbers are reversed. 20 is supposed to be on top, 6 is supposed to be at the bottom. Okay, so all right, very good. That's okay, I got it. So we are looking at 20 choose 6, and that would be ways to 4. Okay, this is important for Jacquard to choose 6 out of 20 possible destinations. Okay, there we go. So now what are we going to do? So now we're going to say, okay, so let's just say that Jacquard chose first, okay, and Jacquard is holding the 6 destinations, and hiding those 6 destinations, and go, hey Londo, it is your turn now, but I'm not going to show you, which 6 destinations I have chosen. So Londo comes along and go like, okay, it's my turn to choose 6 destinations out of the 20 possible destinations, and but we are not interested in how many ways Londo can choose 6 out of 20 possible destinations, because now we are only interested in, okay, out of the 6 destinations that Londo is going to choose, we want 4 that are in common with what Jacquard has chosen, and obviously the other 2 would not be in common, right? The other 2 is not going to be in the intersection of the 2 sets of destinations. So given that is the problem now, what are we going to do? Okay, so I'm going to ask you guys to think about this. Okay, now it is Londo's turn to choose, and Jacquard has already chosen. Okay, so Jacquard already has 6 destinations chosen, and hiding those 6 destinations from Londo, and Londo is now saying, okay, it's my turn to choose. But we are only interested in 4 out of the 6 destinations to be in common. Alright, so Adam is asking, so we are interested in when the cardinality of the intersection is exactly 4, but not at least 4. That is correct. Exactly 4. Because to compute at least 4 is easy, because we can just figure out how to calculate for the case of 4, the case of 5, and the case of 6, add them all together, and then we have at least 4. So we're only dealing with exactly 4 at this point. So that's a very good question, Adam. So given that we are only interested in exactly 4 common destinations, what are we going to do here? Choose 4. Okay, so we know we're dealing with something choose 4, but we also know there's a something choose 2, because remember, there are 2 destinations that are not in common, right? So so I'm going to propose something like this. Okay, so we are looking at something that is I'm going to put an X here because we don't know exactly what to put with the at the place of X. So X is a placeholder. We're going to have to figure it out. So we are dealing with something choose 4 times, okay, and we can use a C dot for times, and this time around we're going to have something else, choose 2. Now why choose 2 and why choose 4? Because the 2, okay, we need to put it back onto the same line. There we go. So the reason why we are choosing 4 is because we only want 4 as the intersection, okay? And the 2 over here is for the ones that are not within the intersection. So the question is, assuming that we already know what Jacquard has chosen as the 6 destinations, the question now is, how many ways can Londo choose out of the 20 possible destinations so that 4 are in common to the 6 that Jakar has chosen, and then the other two are not common to what Jakar has already chosen? Are we kind of understanding the question? Because it's important to clarify the question first. Which direction are we trying to think about this problem? All right. So, what should x be and what should y be? That becomes the question. In other words, we are taking how Jakar is choosing completely out of the equation here. We are basically saying, okay, here are 6 destinations that are already chosen, and of these 6, okay, we want 4 to be in common. I think I just spelled out the answer, didn't I? Because I did say of these 6, we want 4 to be in common. So what do you think x is going to be? X is going to be 6. Okay, x is 6. Okay, so let me just write it here. You guys can focus on the right hand side. You don't have to look at me typing in LaTeX. So I'm going to say x is 6 because we would like to choose 4 that, okay, we would like to be specific. We want Londo to choose 4 of the 6 destinations chosen by Jakar. That is why x is 6. Is that okay? Does everybody understand why x is 6? Because out of the 6 destinations that are already chosen by Jakar, we are trying to figure out how many ways can we choose 4 of those 6 so that we have an intersection of exactly 4 destinations. All right? What about y? Aren't we done already? I mean, why do we have to deal with the other combination here? Because you still have 2 more destinations that you have to choose. But we cannot have those 2 other destinations to be in common. So they have to be in the set other than what Jakar has already chosen. There are 20 destinations as a total. So we are choosing 2 out of how many? What do you think y is going to be? So I'm going to say y is, okay, it's suspense here. 14 is correct. Okay, so Jonathan is correct because y is 14 because the other 2 destinations that Londo is going to choose cannot be in common to the 6 that Jakar has already chosen. Okay, so 20 minus okay, let me be very clear why it is 14, okay? Because it is 20 minus 6. That is why this one is 14. Okay, I'm going to turn this into an equation. All right, cool. All right, so what is this number? Okay, now that we know what x is, now that we know what y is, so now the next question is what exactly is let's see, this is going to be 6 choose 4 times 14 choose 2. What exactly is that? Oh, I forgot a backslash. Let me put the backslash here. There we go. So what exactly is that? Remember, we're dealing with cardinality, right? So this is the cardinality of something. And there are only 2 sets that we're interested in, that I have mentioned. One is the event set E, and the other one is omega. So which one do you think this one is? Oh, that's my piano. The cats were hangry, so they just kind of pounced on the piano to announce their their hunger. Mhm. Combined or just the 14 one? It's the product. We are looking at the product of 6 choose 4 times 14 choose 2. It is the cardinality of something, but whose cardinality are we talking about? And that would be the event set. Okay, so this is the event set. So I'm gonna continue with this part here. This is the cardinality of E. Okay, so I can now turn the question into a statement, like so. Alright, so if that is the case, what do you think is going to be omega? In other words, omega is representing all the possibilities, but all the possibilities simply means we don't really care what Jakar has chosen. Londo just gets to choose whatever he wants. And that's going to be not squared. It is just 20 choose 6. Okay, so I'm going to write it here and then I'll explain it. So the cardinality of omega is just 20 backslash choose 6. There we go. Alright, this looks awfully confusing, isn't it? Because we are looking at two people. Each person gets to choose 6 out of 20 possible destinations. So how can omega be just that? Well, it's a matter of perspective, okay? Because we are basically saying we are just going to let Jakar choose 6 destinations first, and we don't even care with how that is done or how many possible ways there are to have Jakar to choose 6 destinations out of 20. And then we focus on only how Londo is going to choose his 6 destinations, and then out of the 6 destinations that Londo, the second person, is choosing, we want 4 to match exactly, we want the 4 to match the 6, somewhere within the 6 of the destinations chosen by the first person, which is Jakar, and we want the other one not to match any of the chosen destinations from the first person. So it's a matter of perspective. We are just basically throwing, the counting of the first person out because it really does not matter in this case when it comes to the chances. So when it comes to the probability, so the probability of Jakar and Londo um, having 4 common destinations is really just the ratio. Okay, so in this case, it would just be the fraction of as the numerator. It's going to be the product of 6 choose 4 and then 14 choose 2. So let me just write it out here. 6 choose 4 times, what was it, 14 choose 2. And then as the numerator, as the denominator, this is the numerator, and then the denominator is really just the cardinality of omega itself, and we already know that is just 20 choose 6. There we go, and put a and dollar sign. That should turn it into equation, but the fraction, the line of the fraction, is not showing. This is one thing that I don't exactly understand why it is not showing, so I'm going to choose to use a division with a slash instead of a fraction because somehow it doesn't work out. There we go. Alright, so I have the problem solved already. Okay, do we have any questions? And I'm glad that we are having some questions coming up, because that means you guys are thinking, you guys are absorbing what I'm talking about, and you're kind of like, okay, wait, hold on a second here. All right, so the first one is, can you explain how I got x and y one more time? Okay, and then the second one is, I'm still a little confused about why only one person matters for all outcomes. That's okay. So let me explain the first question. Answer the first question first. Can I explain how I got the x being 4, which is x is 6, and then y is 4? No, take it back. X is 6, and then y is 14. Okay, so x choose 6 choose 4 is basically saying, out of the 6 destinations that are already chosen by the first person, I want the second person to match exactly 4 of the 6. That's why it's 4 choose 6. That's why x is 6. But we need the second person to choose 6 destinations total, right? So we have accounted for how many ways to choose 4 that are in common with what the first person has chosen. What about the other 2 destinations? Well, guess what? The other 2 destinations cannot come from the 6 that were chosen by the first person, which leaves us 14 to choose from, because there are 14 destinations that were not chosen by the first person. So that's why x is 6, because it is the cardinality of the destinations, or the set of destinations that the first person has chosen. And then y is 14, because that is the set of 20 destinations minus the set of 6 destinations that were chosen by the first person. So that explains, I hope that explains why x is 6 and y is 14. Is that okay? Yeah, exactly. It is. It's a matter of thinking, right? How you think about it. But a lot of times people forgot about the y choose 2. Okay, they forgot about the other non-matching destinations, and they only deal with the first one. Then we don't have the right number, because we have not taken into consideration how many ways can we choose the non-overlapping destinations. Well, we got to take that into consideration. All right, so that's the first one, and then we're going to answer the second question, which is, I'm still a little confused about why only one person matters. Because it's a perspective, okay? Because it doesn't matter how many ways Jakar can choose the 6 destinations. For each way that Jakar can choose a destination, there are this many ways for Londo to choose his destinations in order to have exactly 4 overlapping. That is why. Because it doesn't matter, because you'll be multiplying 22/6 both to the numerator but also to the denominator, and they just kind of cancel out. In other words, we are looking from the perspective of, let's just say that Jakar, the first person, has already chosen the 6 destinations. And in that case, for each way that the first person can choose a destination, what are the chances that the second person will choose 4 destinations that are the same as the first person? That doesn't change, right? I mean, even though there are so many ways for the first person to choose 6 destinations out of 20 possible destinations, the probability does not change. So for each way the first person can choose 6 destinations, the chances of the second person overlapping 4 destinations with the first one remains exactly the same. So that's why it doesn't matter. I hope this kind of makes sense. It's kind of just the intuitive way of looking at it. All right. Would 3 people, same problem, be the same omega cardinality? Let me think. I have not thought about that, okay? I have not thought about it. So we already know the chances of 2 people. So having the third person, jumping in, so we want an overlap of the same number. It gets a little bit more complicated, okay? Because Oh, I know how to think about this. So it's not any more complicated because the third person is going to use, so what we do is we focus on the intersection. Okay, so we focus on the intersection, but it gets a little bit more complicated because the intersection is between three people, which means it is possible for any two people to have an intersection of more than four. So I think the problem gets significantly more complicated when you're dealing with three people. Fortunately, the lotto problem does not have a third person. So it's a two-party kind of thing. So now what you need to do, okay, is to kind of relate this particular problem with the lotto problem. Because I'm just telling you, it's almost exactly the same thing. You just have to change your perspective and try to match, okay, so what is what? Who is Jakar, okay, and who is Londo when we transition to the lotto problem. I'm not going to give you the answer right away, okay? If you guys cannot figure it out and anyone wants me to give you guys a clue, I can do it on Wednesday, which is also the day when we go over the practice exam for exam 2. But I want you guys to think about this a little bit because being able to see the parallel between two problems, one being solved and one is not solved yet, is really important in computer science. And can anyone, okay, I'm not sure whether you guys know this or not, but I'm just going to try it. Can anyone explain to me why that is important in computer science? Being able to recognize or abstract the common essence between two different problems. So if one problem has a solution and the other problem is almost the same, they actually has the same nature, you can kind of reuse the same solution. To make a genetic algorithm, maybe, but it's a little bit more, so I'm digressing here a little bit. You can look into NP complete problems. Because with NP complete problems, it is an entire classification of problems where every problem can be transformed to another problem within the same category using polynomial time. So that's why what I'm doing here ultimately is important in computer science. You guys will get to NP completeness not at ARC, but when you move on to a 4-year university. Usually that class is called computation theory, that sort of thing. Yep, and to figure out whether if a similar problem is also solvable. Exactly, because if you can solve one problem and you say, oh, but that problem is kind of like this problem, I know how to transform that problem into this problem, hey, guess what? You have that problem solved as well. And that's nice, right? I mean, that's why we have modules and libraries and subroutines, because we are going to be able to share the same solution as much as possible. We don't like to rewrite code unnecessarily. So there is that. All right, so I'm going to consider this problem solved, and your job is to try to figure out how this is going to map to the lotto problem that you need to solve as your homework. All right, excellent. And I think we got one more message coming in. Laziness is built into the science. Laziness is the motivation of the science. Laziness is the whole motivation. I mean, can you imagine a program without the use of subroutines or classes or any type of abstraction mechanism? The whole thing is basically the result of copying and pasting and modifying. That would be horrendous. Yeah, you is right. And we try to come up with as many ways to reuse code as possible. If you think about it, subroutine is kind of the most basic mechanism to reuse something. And then we have methods of objects, we have classes, we have inheritance, we have abstract classes, virtual methods, and so on. All of those, every single one of them, is a mechanism that allows the reuse of code in a different situation. So there you have it. Translate it into assembly for maximum pain. Well, that is my job because I also teach assembly language programming. It's not quite as bad as what people think because the programming language is just changing the basic tool that you can use, but the principle of how you apply the tools can still be the same. So you can still do object-oriented programming in assembly language. It might look a little uglier, but you can still use the same principles. So there's a differentiation between what is limited by the language itself, what you can express or what you cannot express using the programming language, versus discipline, versus how you structure your program. Yep. So there you go. All right. So I'm going to consider this topic done unless people want to bring it back and beat it up a little bit more. So with this done, oh right, I also released a homework for relations. So that one is it's actually quite useful. Okay, I come to think about it, I think this is actually the right time to do it because we have the exam. The exam 2 is going to include relations. It's going to include propositional logic. I haven't quite decided yet whether to include discrete probability. Usually I don't put discrete probability into exam 2, so I probably will not ending up putting discrete probability into exam 2. But since relations is going to be a topic in exam 2, having the homework assigned now is actually in a way better than having it assigned to you way back when, because hey, guess what? Now you have to do the homework, and while you're doing the homework, you're also refreshing the concepts that you have learned about relations, which is perfect. This is like, oh, free studying. You're going to have your excuse to study because you have to do the homework. So there you go. I'm praying for mostly predicate stuff on exam. We haven't gotten to predicate yet. Okay, we only have propositional logic. Predicate logic is after a whole bunch of other stuff. So we're going to talk about big O, big omega, and big theta first, and then we're going to talk about graphs, and then after that we'll get to predicate calculus, which is actually a lot of fun, but the semester is only so long, unfortunately. Oh, okay, yeah, propositional logic. All right, so we are going to now get into big and little o, omega, and theta. It's going to be the Wednesday after this Wednesday. Yeah, after this Wednesday. So November 3rd sounds about right. Let me put it into the calendar of this class, okay, before I forget. There's a way to do it. Let's see. View calendar. I don't like the fact that Canvas, doesn't really integrate with Google Calendar, because it'll be nice if it's integrated. So this way, if I set up something new here, it's gonna pop up in your calendar. Is it actually integrated? Make a script for it. Yeah, well, I can write all the scripts that I want. Without the API key, it will be pointless, because the district is not going to release. It's not going to give me the API key to interact with Canvas. Nope, absolutely not. Are you kidding me? The district does not trust me in any way. Alright, so let me see, how do I set up a new event in the calendar? Oh, the plus sign, right? I mean, yeah, that should be pretty clear. Exam 2 for CISP440. And the date is going to be next Wednesday. There we go. And the time, as usual, is from 4:30 p.m., which is our usual lecture time, to the end of the lecture for everyone, except for people with the DSPS paperwork. And location is going to be online. There we go. And submit. Yeah, going to be the same format. Wilson. It's going to be in the same format. You will have a document that is going to be shared with you, and all the instructions, all the questions are going to be in the document. And I want you guys to type your answers within the document as well, and not copy it from somewhere else. So there's that. All right, so this is done. And now we can go back to the new topic. All right, so the new topic is big O, big omega, and big theta. All right, so this is an interesting topic from the very get-go, because most people have heard about big O, the big O notation, but what most people think of as the big O notation is not very precise. Okay, so big O, big omega, and big theta are concepts that most people think they understand, but they actually don't. So we'll start with the most tedious way to compute the time to complete an algorithm. Okay, so we're going to start with something that is just horrendously, tedious, and then we'll understand why we don't want to do it that way. All right. So the time complexity of an algorithm refers to the amount of time for an algorithm to complete. Okay, and it is usually a function. Okay, it's usually a function. Since we have talked about functions already, so the domain is the size of a problem, and then the range, or the codomain, is the amount of time that it takes to solve a problem of that size. So I'm going to give you a very simple example in this case, which is just adding up all the values of every element in an array. So in this case, I use I as an indexing variable. Sum is just holding the sum of all the items. A is an array with a size of n, and n can be a macro, can be a const, doesn't really matter. N is just a natural number telling us how long or how many items are in the array. It is an array of integers. I starts from 0, some start with 0. As long as I is less than n, for each element in the array, we add the value of the element to sum, and then we add 1 to the index I, and we go back to the beginning of the loop until I is no longer less than or equal to n, and then we're done. Alright, so the algorithm itself is really simple, but I'm only using it to illustrate the concepts. So how much time is it going to take for this algorithm to finish, to complete? And we are talking about the relationship between the amount of time, which is usually measured in some kind of seconds. Okay, can be milliseconds, can be microseconds, can be nanoseconds, but it's going to be in some quantity of seconds. And also the problem size, which in this case is how many elements do we have in the array. So now we're going to look at this algorithm, and we're going to break it up and say, okay, which part is only done exactly once, and which part is going to be in the loop. And for the stuff that is in the loop, there is one thing that we have to do one time more than the rest. Okay, so what I have done here is to use T1, T2, and T3 to denote certain things. And right here it says T1 is for line 4 and 5. So the initialization is going to be when you add up the time to initialize I and to initialize sum, we'll call that time T1. And then T2, okay, T2 indicates the amount of time for each time line 6 executes. So this is line 6, which is the evaluation of the condition of the loop. And then T3 is going to be the time for line 8 and 9 to execute, which is actually the body of the loop. So what is the total amount of time for this algorithm to complete? I call it f of n, and that turns out to be T1 plus T2. T1 only occurs once because that's the initialization, but T2 is here too because there's one extra time that you have to evaluate the condition before you get out of the loop. Okay, so it is executing. So line 6 actually gets to execute 1 time more than lines 8 and 9. And then 8 and 9 would execute exactly n times, but line 6 will also execute exactly n times on top of that 1 time to exit the loop. So the actual total amount of time for this particular algorithm to complete is going to be t1 plus t2 plus n times the sum of t2 and t3. Okay, this is pretty simple stuff, for the most part, just arithmetics. Okay, it's not even algebra. This is just arithmetic, counting. This block is going to execute n times. This block is going to execute n plus 1 times. That block will only execute exactly once, and so on. Okay, so but when you analyze more complicated algorithms, it gets a little bit more complicated. Okay, so when we are dealing with bubble sort, it's going to be a little bit more complicated because there's one component here for initialization, where it only happens once, and then there's another component here that's going to happen, n iterations, and there's another component here that's going to happen n squared times, because bubble sort has a loop inside a loop, so that's why there's a component that is going to execute proportional to the square of the number of elements in the array. And depending on which variant, how you write your loop, T1, T2, and T3 can also change a little bit. Now, how T1, T2, and T3 can change depends on a lot of factors. Okay, I'm not sure how many of you understand how DDR2 or doesn't even limit to DDR2. Any type of the DDR type memory operates. DDR is double data rate. It's basically saying you are making the memory a little bit smarter, so it can get into quote unquote a semi-automatic mode. Typically, when you access memory, it is in quote unquote manual mode, which means every single time you want to access a location, you have to go through all the trouble and say, oh, this is a read operation. That is the address over there that I want to access. And after you specify everything, you tell memory and go like, okay, I want to access that location. And then you have to wait. There's a certain wait time that you have to there's a certain wait time associated with addressing a particular location in memory. After that wait state, then you can read back that location. What if you want to read the next location right after this? Guess what? You have to repeat the whole process. Then you go like, but that's really just the next location. I really should not have to re-specify everything. Well, without DDR technology, that's what you need to do, is to re-specify everything, okay? Which is a lot of waste of time. So DDR basically is just saying, if you want to read a block of memory, like a chunk, all at the same time, just tell me where to start, okay? Once I understand where to start, we'll just make an agreement, okay? Because the system clock is common to memory and also to the processor. So they are just basically, each person, or well, each component is keeping track of its own timing. And they're basically going like, so for every clock transition, rising edge or falling edge, okay, I understand that you're trying to access the next location. I'll have the next location available when we experience the next edge, okay? And so the processor doesn't have to re-specify, hey, this is a read operation, and that's the location I want to access. It just keeps reading. So with more advanced DDR technology, sometimes they can fit a read cycle between the transitions. So timing becomes like super duper important in this case because there's no actual clock transition. So they have to keep track of time very, very well in order to keep all of this stuff synchronized. But nonetheless, okay, the point is, it's only good for reading a block of locations. It's not really useful for reading, oh, here's one location and there's that and that location. So what does that have anything to do with what we are talking about here? Some algorithms access sequential elements that are sequential in an array. So in that case, DDR memory kicks in and go like, wow, this is like perfect because I can just prefetch an entire block of stuff and you're gonna need it eventually. Okay, so it's perfect. Okay, your time complexity is gonna be very small, I mean, at least the portion that depends on memory access is going to be small because you're making use of this beneficial feature that we call DDR, double data rate. On the other hand, there are some algorithms where the access of an array is all over the place. Well, guess what? Quicksort is one of those. Okay. So when you deal with an algorithm where it goes like, I want to go here, and then I want to go there, and then I want to go there, and then I want to go there, DDR technology is not going to be very helpful because the locations that you're trying to access is all over the place. It's not sequential in any way. So in that case, you may not be benefiting as much from the use of DDR type memory. And as a result, the coefficients of these times, these, T1, T2, and T3 can vary. Okay. Shell sort, I'm not sure. Okay, I can only I can only hold so many inefficient sorting algorithms in my head, but I can tell you one really amazing algorithm that was invented back in the mainframe days that actually in today's technology it worked really well on tapes. Okay, and most of you are way too young, and even your parents are way too young to remember tapes that are used on computers to store data. It's called, no, it's not radix. It is merge sort. Okay, so merge sort was invented, I would say, specifically for computer or mainframe computers that were using tapes, and it was super efficient. Okay, you only need 3 tapes in order for this to work. So you start with one input tape, and then you split it into, that's why it's called merge sort, because you have a split and then a merge phase. So you split the one tape into 2 tapes, and then you merge the 2 tapes back into one tape, and then you keep splitting and merging and splitting and merging, and then eventually it'll be sorted. Okay, but the point is, every single time you split a tape, you are sequentially reading one tape and you're sequentially writing to the other 2 tapes. Every time you merge, you're doing exactly the opposite. You're reading sequentially from 2 tapes and you're writing sequentially to 1 tape. The key word here is sequential. Every single access to the array or tape is sequential. And that is great for DDR type memory because we are just having a whole bunch of sequential operations. We get to one location, we get to the next location, and then we get to the next location after that, and so on. So, but do we really want to take all of that stuff into consideration when we just want to compare 2 algorithms? Usually, no. Okay, so usually we don't need to take into consideration of how the DDR type memory of a computer is utilized or not. Okay. Typically, we just want to know, generally speaking, is this a good algorithm to use? So when we're dealing with complex algorithms, okay, like quicksort is actually fairly complex to analyze because quicksort depends a lot on where the pivots are. Because if you choose the pivots at the wrong places, it can actually be very slow. Or if the data to begin with, if the array to begin with has a particular pattern and then you choose the pivot point at the wrong places, it can actually be very slow. So some algorithms can be very difficult to analyze, and on top of that, if you want to take into consideration of the hardware aspect, including branches, okay, because at the lowest level, branching is very expensive, okay, because when a processor is pipelined, it already has instructions, quote unquote, in the pipe being partially executed, and if you need to change direction, like because of a conditional branch, then the processor there are 2 approaches to this. One is it has to abort the pipe, which means some of the work that's already done, now we cannot do that. Okay, you just have to abort whatever is partially computed and then start from scratch. The other one is to basically use the hardware to pursue both branches at the same time. Maybe we'll branch, maybe we won't branch, and then the hardware can maintain 2 separate pipes, and then by the time you make the decision, it abort one of the pipes so that the other one is still correct, and you can keep moving on. But nonetheless, the point is it is expensive. Okay, it's either expensive in terms of time or it is expensive in terms of silicon. So that means if your sorting algorithm or whatever algorithm you're writing involves a lot of branching, it is not going to be as efficient as algorithms that have fewer branches. Okay, so if you take everything into consideration, we are looking at some really complex way to compute all of these time constants, and you might end up with uh, a a function that has all kinds of terms. Okay, not really just n and n squared. You might have the log of n. You might have some really weird mathematical function on n itself. But all of that really should not matter. Okay, when we are just comparing whether an algorithm is at least as good as or not as good as another algorithm. Okay, I'm going back to the text channel because stuff has happened over there. 4 tapes, not 3. Nope, you only need 3. You only need 3 tapes because you flip the tapes around. So you have one input, and then when you split, you have the 2 output tapes. And then when you are merging, you turn it around, and then the 2 output tapes would become, the 2 output tapes will become the inputs, and then the 1 input tape would become the output. So basically, you just need 3 tapes to do merge sort. What about recursion? Yeah, recursion is bad. Now, the implementation of recursion can be bad. Okay, I should put it that way. Because if you have tail end recursion, which means the recursion is at the very end of the function that's calling itself, it doesn't have to be bad because it depends on implementation. Now, when you're doing this in C and C++, you don't have a choice because the compiler will always create a new call frame. Now, if you don't know what I'm talking about, that's okay. Okay, I'm just saying that there's an overhead associated with a recursive call, and you can potentially run out of stack space because of that. On the other hand, if you're dealing with a programming language where the language itself or the interpreter itself has the capability of recognizing a tail end recursion, then it would just say, I'm turning this into a loop. Okay, where it doesn't make a new call frame every single time because it doesn't need to. Okay, because when your recursive call is at the very end and there's only one point of recursion, it becomes just a loop. So depending on the implementation of how recursion is taken care of, it can be expensive because you're basically putting a lot of stuff on the stack and then popping a lot of stuff on the stack unnecessarily. Or if the language is more efficient with recursive stuff, it may not really incur a lot of expenses either. So that's a good point. But what I'm trying to say here in this particular module is none of that really should matter, okay, unless you're talking about 2 algorithms that have the same quote-unquote time complexity, which we'll talk about later. What is time complexity? By the time this f of n, as time complexity is the exact time, okay, but a lot of times we don't need to know exactly how much time. We just need to be able to compare 2 algorithms. So when you have 2 algorithms, okay, using what we loosely use as the big O notation, so if 2 algorithms have the same big O time complexity, and then later on we'll find out why big O is really not the best term to use, but we'll just use the casual way of using the big O notation. Then you can look into all of these nuances. Okay, so if you look at heap sort and you look at merge sort, both of those have n log n as the time complexity. Then you can look into, but which one is more efficient when we are using DDR type memory, which one is more efficient when we have pipelining, blah 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 blah. So you can fine tune and actually be picky about which one you actually want to use. But when you're comparing bubble sort versus any one of those sorting algorithms using n log n time complexity, there's no comparison. Unless you have a very small array to sort, then it doesn't really matter one way or another. All right. So yes, I digress a little bit, okay, but all of these digression at some point will pop up in your future computer science classes. Now, whether you can remember that we talked about all of this stuff here is a whole different question. All right, so when we compare algorithms, most of the time we just want to look at the quote-unquote shape of the curve. Okay, I'm using that term in a very, very loose way. Okay, we just want to look at the shape of the curve and look at the shape of the curves when we're comparing 2 different algorithms. So we can lose some of the unnecessary details, okay? And basically, in mathematical terms, we are looking at the basically it's called the asymptotic behavior of a function. In other words, when n gets very, very big, what are we looking at? That's what we are asking. So to have the vocabulary to look at asymptotic estimates, we're going to introduce a whole bunch of terms, and each one is a little bit cryptic, especially the way I explain it, because I'm using all the same stuff that we have been using since the beginning of the semester. Quantified expressions, okay? Because that stuff is very, very useful, okay? And you kind of have to get used to it. Nope, we're not going to do row today. So we're going to keep going, okay? No row taking today. Alright, so the first thing we are going to talk about here would be, let's f of n defined to be the actual time complexity of an algorithm. So f of n itself can have a lot of tiny little terms. It has a constant term, it has one term that's proportional to n, one term that's proportional to n squared, one term that is proportional to log of n, one term that's proportional to n log n. It has just a bunch of components. Ugly. And then g of n is going to be a simpler approximation of the time complexity of an algorithm. So g of n typically looks very nice, like just n itself, or 1 for a constant time algorithm, constant time complexity, or it can be n squared, can be 2 to the power of n, if you have a really bad algorithm that has the exponent to it, or if you have something that's even worse, it can be n factorial. Yeah, n factorial is really bad. It's worse than exponential. So, so what are we talking about here? Okay, so we have one that is exact, one is proposed as an estimate. Okay, so what we want to do is to find out how those two are going to relate. Okay, and the relationship between the actual versus the estimate is what we are looking at. Okay, we want to find a g that is going to be a very tight fit for this particular f, which is going to look very ugly, lots of terms, and most of the terms do not matter. Okay. Alright, so the first term we're going to have to introduce is called supremum. Supremum. There we go. And in this case, we are going to make it as, sorry about that. We're going to make it as general as possible. So I'm using, the term supremum. And you can, later on, I'll talk about, what, well, actually in the notes, I already used the term and say, well, for the most part, you can see it as, what a term that you're already familiar with. But let's not get there first, okay? So we'll just say that, a set A is a partial order. I hope you guys still remember what a partial order is. If not, that's okay, because your homework assignment that's due in a week is gonna talk a little bit about partial order, because that's a relation. Okay, so partial order basically means this means we can define the less than or equal to relation for the Cartesian product of A and A itself, and it is going to be reflexive, it's going to be antisymmetric, and it's going to be transitive. Yes, those terms we have all talked about those already. Yes, smooth versus rich. At least as good as. Okay, that's basically what greater than or equal to or less than or equal to means. I think so. I think the beer commercial makes it easy to remember, and it's fun too. Probably not very politically correct in today's world, but and if it works, it works. Alright, so we want a set that is partially ordered, because if it's not partially ordered, we cannot define what a supremum is. Now we're going to define a subset X of A. So A is already partially ordered, and we are choosing a subset X from A. And this means X has some of the values of X. let's define the predicate p, y, x. Okay, y is in lowercase, x in uppercase, to be the following. Okay, this one is not too hard to understand, right? Because we have just one universally quantified quantifier, which is for all x in uppercase x, which is a subset of a, x is less than or equal to y. Okay, this is the predicate. In other words, all it is asking is y at least as big as all of the elements of x? That's what p is asking. Okay, but to put it in a very concise and precise way, we can use this particular quantified expression. Are we okay so far? Does everybody understand what the predicate p is trying to express? It's not quite the maximum. It's simply asking, given a particular y, is y at least as large as everything else in x? Okay. Nope, y is not in x. So y is basically an upper bound of x. Okay, so if p is true, okay, if p comes back and say, yeah, this quantified expression is actually true, then we can say, oh, okay, so now we can say y is an upper bound of x. Now y itself doesn't have to be an element of x. It has to be an element of a, but it doesn't have to be an element of x. Okay, so it is just an upper bound. Now, when we talk about an upper bound, it can be a very gross upper bound. Okay, so let's just think about the values of a dice. Okay, of a six-faced regular dice. Okay, 1, 2, 3, 4, 5, 6. So in that case, what about 20? Okay, is 20 the upper bound of the values that can that can be a value whatever side the dice is facing up? Okay, the answer is yes. Okay, because none of the value of a dice can even come close to 20. But 20 is still called an upper bound of all of the values that a dice can show, unless you have a 20-sided dice, right? And there are such things, but we are not talking about a 20-sided dice here. All right, so we're going to define, s. The variable name s is the supremum of x, and s is a supremum of x if and only if, okay, s is an upper bound of x, and on top of that, now this part is easy, right? We already know what pyx means, because pyx simply means that y is an upper bound of the set x. So in this case, s has to be an upper bound of x. Okay, not a problem. But there's one extra requirement that we want here. The extra requirement is also a universally quantified statement, which is for all s prime. Now s prime has nothing to do with s. Okay, it's just I'm just picking another variable name s prime. For all s prime, p s prime x implies s is less than or equal to s prime. Okay, so what does that mean? Now, what I did not specify here that I probably should have specified is s prime has to come from the set A. It doesn't have to come from x, but it has to come from A. Because otherwise, the partial relationship may not be defined between, we may not be able to compare anymore. So s prime has to be coming from A, but not necessarily from x. So assuming that we add that statement here, that s prime has to come from A, so we can at least define less than or equal to. Can anyone kind of tell me what this means here? For every s prime coming from A, if s prime is an upper bound of x, we want s, which is the value that we are trying to qualify here, has to be less than or equal to s prime. So we are looking at all the upper bounds, and we want all the upper bounds to be greater than or equal to s. What is that saying? I mean, if you read the sentence right next to this, that explains it already. We're looking for the minimum upper bound of x. Of all the upper bounds, we want the one that is the smallest. Are we doing okay? So the supremum of x really just means give me the smallest upper bound of the values in X. That's all. Which you already know, okay, in a very limited context, you know it as the maximum of the set X. So now some of you are already thinking, it's like, why didn't you just say that? Why do we have to understand what is supremum when it is really the same thing as the maximum? Well, it's not exactly the same, okay? Because maximum can only be defined when you have a I just cannot remember the term. Partially ordered versus totally ordered. There we go. So maximum is only defined when you have a totally ordered set X, okay? Whereas the set has a totally ordered relation of less than or equal to. But supremum can be defined with anything that is at least just partially ordered. So that means there are cases where you can find a supremum, but you cannot find a maximum. Is that okay? Does everybody kind of at least get a general idea of what I just said? Say it one more time? Sure, absolutely. A supremum can be defined for any set A that is partially ordered by some kind of a less than or equal to relation, as opposed to maximum can only be defined if A is a totally ordered set over when you have a less than or equal to relation that is totally ordered with respect to the set A. And totally ordered is more restrictive because in order for something to be totally ordered, it has to be partially ordered first. So there are certain sets where you cannot find a maximum, but you can still find a supremum. The beer commercial comes to mind. The beer commercial, when we talk about the characters in the beer commercial, the relation that we call at least as attractive as is a partial order because we cannot compare the guy who is rich but not smooth versus the guy who is smooth but not rich. The relationship, who is more attractive between those two, was undefined. And that's why it is not a totally ordered set, because there are certain things that we say, well, we don't really know how these two order. But of the things that are indeed ordered, they will follow these three restrictions here. One is being reflexive. Every element relates to itself. Okay, that kind of makes sense, right? If you pick any person and you ask, is that person at least as attractive as the same person? The answer is, yeah, quite obviously. Why did you ask, right? So reflexive is one of the properties that we need in partial order. Antisymmetric is the other one. Antisymmetric, to quickly summarize, not to get into the quantified expression, is basically saying if A relates to B and B relates to A, then A and B must be the same. Okay, that's antisymmetric. So what that means if Tom is at least as attractive as Harry and Harry is at least as attractive as Tom, then Tom and Harry are the same. They have the same attractiveness. Okay, that kind of makes sense. And then they're transitive as well. Okay, and transitive is basically saying if A is at least as attractive as B and B is at least as attractive as C, then A is at least as attractive as C. That's transitive. These three are the only three that are needed in order for a relation to be partially ordered. To be totally ordered, then we have to add one extra requirement, which is basically saying if I choose any two things out of A, we have to be able to find out which one relates to which one. Okay, it has to be one way or the other, cannot be neither. Are we kind of vaguely remembering that discussion when we talked about relations? Yes. Okay, excellent. So, getting back to here, so supremum is actually a more general term because it is it works on any set that has a relation that is just partially ordered instead of totally ordered. However, given the context that we are in, we're talking about time, and time is usually measured by a real number, and the set of real numbers, when you look at the less than or equal to relation over the set of real numbers, it is totally ordered. So from that standpoint, when I talk about supremum, you can basically just think of maximum, because the set that we are dealing with, the real number set, is totally ordered under the relation of less than or equal to. All right, so I'm just looking at the time here. We got about 4 minutes. So infimum is the opposite. In other words, just look at it as minimum. So now we have maximum and we have minimum. And then section 3.3 talks about a concept that most of you should already understand because you have taken pre-calc. And I was kind of reminded that some people may not have understood limit in a pre-calc class. So I'm just going to spend the next 4 minutes to try to see if you guys understand what is the limit of a sequence. So a sequence is basically a tuple, a very, very, very large tuple. So all the elements within a sequence, ordering is important. Okay, there is such a thing called the first one, the second one, the third one, and so on. So what we really want to know is this particular expression here. So if we take a limit where the index I goes to infinity, and the expression that we are interested in is just xi. So we are not even looking at a function of the summation or anything crazy like that. We're just looking at xi. What does that mean? Okay, if I just say that as the index goes to infinity, xi approaches k. What does that mean? Well, what that means is this. Another nested statement that has quantifiers. Okay, so let's take a look at this this particular statement. We only got about 3 minutes left. I think we barely got enough time to look at this one and understand what that means. Okay, so we start from the outside. It's a universal quantifier with epsilon. And this is a shorthand to say for all epsilon that is greater than 0, that's a real number. Or I should say the other way, bad grammar there. For all epsilon which is a real number that is greater than 0, the following has to be true. Okay, if I can say that k is the limit of xi as I approaches infinity, then this part has to be true. Whatever is inside here has to be true for all epsilon that is greater than 0. Okay, so let's look at the nested portion of this quantified expression. This one here says there exists an m that is a natural number. Basically, m is a valid index into the sequence, such that, and now we have yet another level of universal quantifier here. For every j that is greater than or equal to m, and j has to be a natural number, now we look at the actual core part of the whole thing. So we are 3 levels nested in quantifiers. But all we really want to say is k minus x of j, take the absolute value of that, has to be less than epsilon. So I'm going to ask a question because it boils down to, do you understand what this is saying? Okay, we got one confirmation. What about the rest of the class? So I'm going to explain it, okay, using the 1 minute left, okay? All this is saying is, if this is true, okay, if k is indeed the limit of xi when I approaches infinity, then this statement is going to be true. Okay, so what that means is you can give me any epsilon. Okay, it can be very small, like 0.0001. Okay, give me any epsilon that is a real number that is greater than 0. Okay, and then I will say I can find a particular index, let's say 2000. Okay, so that if you go beyond x of 2000, or at least x 2000, then k minus whatever x x of j is, j is at least 2000, so it can be 2001, 2002, 2003, 6,000, 10,000, 20,000, 6 billion, whatever. Okay, k minus that particular value of x in the sequence is always going to be less than epsilon. Okay, so in other words, the whole thing is going to get closer and closer and closer to k, and so that's basically the idea of a limit from. I think pre-calc should talk about this concept. Okay, so Aman said, sort of remember this, reminds me of epsilon delta proof. Exactly. So epsilon delta proof is very useful when you're dealing with differentiation. This is not about differentiation. This is a lot easier than differentiation. All this is saying is, as once we get beyond a certain point, everything is at least as close to k as within epsilon. Okay, they're all within epsilon away from k. That's all it's saying. In other words, it can be approaching from the positive end, it can approach from the negative end. It doesn't matter. After a certain point, everything is going to be within epsilon away from k. If you pick a smaller epsilon, all I have to do is to move it down the line a little bit. Okay, I'm going to pick a larger m, and I'll still be able to find the m where everything beyond that point are within plus or minus epsilon away from k. That's all it's saying. Okay. All right. So we are running out of time. I'm going to stop here. You have 2 homework assignments. Okay, not one. There are 2. The first one is about counting. It's about the lotto problem. And what you want to do is to basically watch the video if you need to, and think about how the problem that I solved today relates to the lottery problem. The second one is a relation thing. That's basically a concept that we talked about a few weeks ago. But since it's going to be in the second exam, this is a good chance for you guys to review the material. So that's it for today. I'm going to stay online, as office hour for the next hour or so. So if you guys have any questions, just go ahead and use Discord to contact me. But other than that, the practice exam will be posted. Sure, absolutely. So I will go ahead and post the practice exam from last semester, so that you guys have an idea of what kind of question I asked last semester. Sure, absolutely. Alrighty, I'll see you guys on Wednesday. So don't forget about the homework assignment, because if you don't start, you won't be able to ask questions. Alrighty. Okay, good night.